is Mark Baynham. I am with Microchip Technology. I sit in Novi, Michigan, just outside of Detroit, Michigan. I've been with the company for nearly 25 years. My role here is customer facing, so I help our clients, and my specific area of work is in functional safety. So I lead a worldwide group of client facing functional safety engineers. And our goal at the end of the day is to help customers use our products and also to achieve their functional safety requirements. I'll go ahead and shut off the video to save the bandwidth. So my focus today is on functional safety hardware. And I believe Louis going to cover functional safety software in the next presentation. So I think this is maybe a good division. Hopefully you'll learn a thing or two. It's a very challenging topic, and it's very difficult to cover in the 30-minute time slot, but we'll do our best. And we'll start out with a definition of functional safety. And I hope that's not too high level, but it's important to get everybody on the same page. So functional safety intends to minimize risk caused by electrical or electronic systems by addressing both systematic concerns and random hardware faults. And by minimize risk, I mean minimize risk to people, so harm, or we're trying to reduce the harm, either directly by the system or indirectly by damage to the environment. So how do we do that? Well, we can minimize any systematic concerns or systemic concerns by using robust design processes. So when we're developing our architectures, when we're developing our hardware, when we're developing our software, we use design processes that help us avoid any sort of safety concerns. On the hardware side, we look at essentially detecting any sort of random hardware failures. And if we do detect a random hardware failure, we move to a safe state before the hazard has a chance to occur. So there is a time element. So we have to do things in a timely fashion. And then, of course, at the end, when we're done with our work, how do we know that the system is safe enough? And that's really the question that I'm going to try to answer today. And the answer is that we need to do some math, and we need to ensure that any residual risk or risk that's left over after we use the process to mitigate that risk is less than the tolerable risk. And we can't eliminate all risk, so tolerable risk is the risk that society deems to be acceptable. So there are challenges in functional safety, and I have an automotive example here, pretty straightforward. But in time, we started out back in the 70s, where cars went from being 100% mechanical to adding electronic controls around things like fuel injection, anti-lock braking, transmission control. In the 80s timeframe, we had transmission controls that moved from mechanical to electronic. We added traction control. Then we added things like electronic stability control, electronic restraints, electronic steering. We even moved into hybrid power systems. Going forward into the 90s, we had electric power architectures in vehicles, electric vehicles. We added things like adaptive cruise control, more ADAS systems. And then, going to today, where we have things like steer by wire and brake by wire and communications over more networks, over the air, like vehicle to infrastructure or vehicle to vehicle. Over the air updates is another thing that we see today that we didn't have years ago. And the backbone between many of these systems is the CAN network. Of course, The electronic stability control needs to talk to the ABS system, that if you get into a skid, it can apply braking at the right wheels. So this CAN network is extremely important in that. And because of this, the development effort, the effort it takes to develop systems, the car being the ultimate system, it has increased, I'll say exponentially, even though I didn't draw an exponential curve. So the key concept here is that the CAN network is likely safety critical at a very high safety integrity level. So what is a safety integrity level? This is ISO 26262. I pulled this chart right from ISO 26262, which is the safety standard for road vehicles. The safety integrity level is determined by three factors: the severity, the controllability, and the exposure. So the severity, exposure, controllability, super quick example, if you have an airbag that goes off as you're driving down the highway in a vehicle, so that would be, the severity would be very severe. Actually, let me pull this up. So the severity would be life-threatening or survival uncertain. If your airbag goes off, the controllability would be very difficult to control, uncontrollable. You're probably going to get into an accident. And the exposure of driving down the road at highway speeds is high, because that's where we spend a lot of our time, is driving down the roads at a highway speed if we're not in a traffic jam. And that all comes together to be ASIL D. Conversely, if you look at an airbag not deploying when it's supposed to, so if we're driving down an icy road and we slide into the guardrail or into a pole, and the airbag doesn't go off even though it should have, again, we're in a very bad situation. So we have, controllability is it's uncontrollable. The severity is very high, but the exposure of driving into a pole is either very low or low. So the ASIL, or the safety integrity level for that type of a hazard, is quite a bit lower. I mentioned I sit in Detroit, Michigan, so my presentation is automotive heavy. However, I did want to mention that the SIL level from IEC 61508 is very similar. So in IEC 61508 or IEC 61511, which is industrial processing, we have a very similar sort of a formula where we get the safety integrity level from. Slightly different terminology, but overall, we have a similar way that we get the safety integrity level. So the key concept here is that the safety integrity level is determined by a hazard analysis risk assessment. It's typically performed by some sort of an OEM, somebody that's overseeing a project. They're actually looking at the hazards, and they're assigning severity levels or SIL levels, safety integrity levels, to those. So once we know the safety integrity level, and we're going to assume that it's pretty high for this data that we're moving around on the CAN network, ISO 26262 gives us some specific metrics that we need to achieve. So for ASIL B, which we saw on the chart, was maybe something that's not life-threatening, or maybe something that doesn't happen very often. It gives us a single point fault metric of greater than or equal to 90%. These really boil down to diagnostic coverage. So the diagnostic coverage feeds into the formulas that determine these metrics. So single point fault metric is pretty self-explanatory, a single point of failure. Latent fault metric is more of a hidden fault. So these are the safety mechanisms themselves failing. So if I have something that's monitoring the memory on my microcontroller and that mechanism stops working, that would be considered a latent fault. So any sort of exact analysis requires the use of an FMEDA. So FMEDA is failure mode effects diagnostic analysis. And that's a pretty standard tool across automotive, industrial, whatever industry. That's a very powerful tool. When we move up to ASIL-D, and I realize there's a typo on the slide, I apologize. It's ASIL-D, not ASIC-D. When we move up to ASIL-D, our single point fault metric hits 99%. And to get there, we need very high diagnostic coverage. So our key concept here is that fit and diagnostic targets are defined for us in the standards, whether it's ISO 26262 or IEC 61508 for industrial. We have other terms that we use in industrial, like safe failure fraction or dangerous failure, things like that. But overall, really the same basic meaning. Fit rate, I didn't mention what fit rate was. It's failure in time. So one fit is one failure in 1 billion device hours. And by using this FMEDA, we're actually able to assign those failures or the failure rates to different blocks of hardware. And we can actually go in and analyze those blocks and figure out if we can achieve these metrics. So fault detection, either on CAN network or maybe on just generic hardware. In case of a fault, we mitigate that fault, and we mitigate means reduce its effects. And at that time, once we detect that there's a fault, we cannot provide full operation. There are schools of thought, and it depends on what industry you're in and what your application is. You can fail safe, which is the mode of operation that I'm most familiar with is where you either shut the system down or you go into some sort of a predictable operation, like a limp home mode or a reduced functional mode. There's also fail operational, which is a completely different topic. So fail operational, a good example of where you need fail operational is in the controls of an airplane. If you have a fault in a system that controls an airplane, you probably need some sort of triple redundancy to continue to operate. And that's really outside the scope of the discussion today. So once we detect this failure, we get into our safe state with some kind of predictable operation that might include just shutting the system off. But at the same time, we need to inform the user that there's a problem and the system operation is either halted or degraded. That could be turning out a light. It could also be something that's detectable by the user. So if your power steering goes out, you can feel that in your car that it's no longer under control power steering. So you don't need a light for that. Anyway, so how do you detect these failures? And again, this is from the hardware side, we're looking at random hardware failures. Well, we need to monitor to observe the system at a regular interval. We need some kind of a safety mechanism in place that can look for these single points of failure and determine that something went wrong in time to react. A really good way to monitor a system, or in some instances required, we need some kind of redundant system to ensure that we can see a difference if there's a failure. So Sensors, for example, sometimes you need two sensors that have this, that are monitoring the same signal. So you can see if that, if one of those sensors has failed. So looking at an example, a microcontroller sends data using CAN to a host controller. How can we tell with confidence that data is reliable? A few different ways we can do that. We can look for corrupted data by including some kind of checksum. Of course, CAN has an inherent checksum, which is very useful, and we can use that. Some systems or some safety mechanisms might require not only the inherent checksum in the CAN bus, but it might have to have some larger checksum around the data to protect it. We could also have a stuck gap fault, so the data could be stale. The microcontroller that's sending the data might be sending the same data over and over again. So to find that fault, we could include some kind of a counter or a timestamp. We could add that into the data payload. If the data is missing, so for example, if the trace on the printed circuit board is broken, we can detect that fault by broadcasting data on a regular basis or including some sort of a heartbeat in that data stream. We could also replicate the communication channel. So that would, having two separate communication channels or redundant communication channel would also help us detect that missing data fault. Or we could regularly perform an exhaustive test pattern, or we could have complete system redundancy. We could have multiple sensors, multiple microcontrollers, multiple CAN buses, multiple hosts receiving the data, comparing. That's an interesting concept. So this redundancy concept, let's dig into this a little bit. There are a few types of redundancy, right? We have structural redundancy. I think we're all probably familiar with that one, where we have parallel and identical structures performing the same task. The ideal example of that would be a microcontroller with multiple cores running in lockstep. So if we have lockstep cores, those are parallel and identical structures performing the same task. If those are both doing calculations and one has an answer that's different than the other one, there's obviously a problem in the system and we need to get to our safe state. So again, that's fail safe. We don't try to continue to operate. We just say, hey, there's a fault. We're gonna shut down. We're gonna get to our safe state. There's functional redundancy, which is parallel and diverse hardware structures that are applied to a single task. Diversity is a powerful tool where we can helps us eliminate things like single cause failures. So if we have two different microcontrollers running on the same task, that would prevent something like a software bug from causing failures in both at the same time. Temporal redundancy is a powerful one as well. This is where we do the same thing with the same hardware, but we do it at different times. So there are a lot of arguments that say that, hey, temporal redundancy is as good as some of these other redundancies. And actually, going back to my first example of a dual core microcontroller running in lockstep, a lot of times those lockstep cores are actually running out of phase, meaning that there is a temporal redundancy there because core number one does an operation and a few cycles later, core number two does the same operation. That prevents things like a single event upset from a gamma ray or a particle of some sort from causing a common cause failure. There's also informational redundancy. This is where we send extra information that's included with the data and checked for coherency, such as some sort of parity bit or CRC or um, even ECC. So we can correct errors and things like that. So how do I know if my coverage, my diagnostic coverage that I'm implementing, how do I know if that's sufficient? So the easiest way to do it, or the easiest way to make sure that we're going to be able to achieve this high ASIL or high SIL level, is to look at the diagnostic coverages from a specification standpoint. So the ISO spec, other specs have information in them that we can use. In ISO 26262, they provide 3 levels of coverage: low, medium, and high. Low coverage is 60%, medium coverage is 90%, and high diagnostic coverage is 99%. In our example, or what we're talking about today, if we're trying to use the CAN network to achieve some sort of high SIL level, we're going to need to ensure that we have diagnostic coverage at this 99% level. So the ISO spec, as I mentioned, includes a lot of information that we can use on coverages, diagnostic coverages. In part 5 of the standard, there's an entire appendix D that goes through things like communication bus. Part 11 is a little bit more geared towards semiconductors, and it looks at chunks of controllers like memories, sequential logic, analog components, and analog to digital converters. So that part 5 is really looking at the system level, and part 11 is looking at the controller level, or the MCU or MPU level. This is the table right out of ISO 26262, and it gives us some great information here. So we said we needed high diagnostic coverage. Here we go. It's going to tell us, here's your typical diagnostic coverage that's considered achievable. If we're just doing some of these maybe more simple communication techniques or safety mechanisms and communication techniques, we can achieve low and medium. But when we get up to complete hardware redundancy here, we can have a high diagnostic coverage. Or if we do this extensive test pattern, we can have a high diagnostic coverage. But there's one down here that I really want to point out, and that's a combination of some of the other ones that don't provide medium diagnostic coverage on their own. But when we combine those, we can achieve a high diagnostic coverage. So, for example, here we're talking about information redundancy, frame counters, and timeout monitoring, which we looked at earlier in our example. So our key concepts here are redundancy and safety mechanisms and diagnostic coverage. These requirements for all of these things come from the hazard analysis risk assessment. So the hazard analysis risk assessment, when we determine what the hazard is, we assign the SIL level. We define safety goals; those inherit the SIL level. When we define functional safety requirements, those inherit the SIL level. When we get down here to the hardware and software requirements, those also inherit the SIL level. So one thing that we can do is that we can decompose those requirements. So when we look at the requirements that we're given, hey, transfer the data from point A to point B with a high reliability or a quality factor, we can look at that requirement and we can decompose it. And we can decompose it into requirements like, hey, include a heartbeat, include this extra information to protect the data. And when we're applying that decomposition, we can decompose ASIL D in our example here into ASIL B plus ASIL B. So we add redundancy. So we have to use redundant hardware to be able to employ this decomposition. So when we decompose a fail-safe ASIL D system, we can use elements that satisfy ASIL B requirements. Pretty powerful stuff. So the decomposition implied some sort of redundancy. So when we're done with our decomposition, decomposing the requirements and proposing an architecture, we have to make sure that a couple of things. We have to make sure that we're sufficiently independent, meaning that there aren't any common cause failures. And then we need to also perform a dependent failure analysis. This is an important one for software. So the concept there is decomposition. A super quick case study. So we have a system where we need to get information from a sensor into a host controller at a very high SIL level. Maybe it's SIL 3, maybe it's ASIL D. So when we looked at how we do this, we came up with, hey, we're going to need redundant sensors. We don't have a sensor that can achieve ASIL D on its own. So we're going to need a couple of sensors to do this. We've actually incorporated some diversity here. So we have one sensor that's a Hall effect sensor and one that's an inductive sensor. And now we have a couple of MCUs or ECUs, and we're cross-checking the data between the two. And now our goal is to get this over to the host. So we can do that through redundancy. So we can have two CAN transceivers on this side. We can have two CAN transceivers on this side. The host would also need to be running or capable of this high SIL level. And we could transmit the data completely redundantly. That would give us a high diagnostic coverage and probably enable us to achieve this goal. However, that's really expensive, and we're going to add wiring. We're going to add a lot of expense to the system. So maybe there's another way we can approach this. Let's take a look at doing some decomposition. So we have a safety requirement here that says that the sensor shall send sensor position data to host controller ASIL D with technical safety requirements. Technical safety requirement over here is, hey, ECU1 shall send the position data to the host ASIL D. Well, let's look at how we could decompose that. We could say, oh, well, it's going to do it, but it's going to have a requirement here that we need to send this extra information. We need to have a heartbeat, and we need to have some kind of a counter or timestamp along with it. And that CAN transceiver, now we go from ASIL D to ASIL B, ASIL B, ASIL B, and quality managed, which means there aren't any functional safety requirements. So we went from a redundant system to a single system, but we included information redundancy, frame counter, and timeout monitoring. So really what we're talking about here is end-to-end data protection. Hopefully that puts a little bit of a spotlight on what end-to-end data protection is. And just a couple of closing comments, satisfying safety goals. The safety goals and the SIL levels dictate what safety features are required in the application. Safety goals are functional requirements that impact the safety to measure position and send it to the host in this case. The robust implementation of the safety goals provides the diagnostic coverage that we need that allows us to do our math and calculate that, hey, everything looks good. If you're doing this design work, if you're in doubt, focus on the engineering. We all know how to make robust applications. CAN is the heart of a lot of robust applications, but review the design patterns and the diagnostic options. And if you haven't been given all of the failures that can occur from the OEM, focus on that. What can we do to detect failures? And then at the end, use FMEDAs to evaluate what coverage is attained. Some links here to some microchip information on functional safety. Also, for our CAN transceivers, we have functional safety manuals available. The functional safety manual really is a guide to the integrator on how to implement a CAN network safely. The table of contents here, and again, you'll get these slides so you can look through those in detail. And then we also offer FMEDA reports on the transceivers themselves, on the controllers, and on the microcontrollers. And these are what you'll use to build your own system level FMEA.